Yes, Debashish, you can start.
Yeah, thank you, Mike. Is my screen visible?
Yes, it is visible.
Okay. Good morning. So I'm gonna continue from the last session where I discussed introduced this code, the user interface code to you, which is called TPLS, the first level set. Just a quick recap. This is diffuse interface code that solves Canhillier equation and able to solve all kind of multi-phase problems with or without phase change, and specifically in a very high resolution and 3D configuration. And so just gonna go through a little bit. So we have in TPLS this main source files where each file corresponds to each solver, like Canhillier solver for the Canhillier equation, and momentum solver U, V, W for now the momentum equation in X, Y, and Z direction. Then you have two-phase initialization to initialize the domain with all the variables. The pressure solver for pressure, temperature solver for the energy equation. The main NS hybrid is a main time loop file where you call every solver and basically the main code. And so today I'm gonna a little bit discuss about this file, which is called Vapor. So let's just go to droplet evaporation. So what is happening here is you have a droplet in the domain and it's evaporating. And the droplet is placed on a heated surface. So, yeah, the droplet is placed on a heated surface. So in the surrounding, we have the gaseous mixture where you have the inert gas and as well as the vapor of the liquid that is evaporating. So you have two vapor components here. And you have the liquid. So CL is the volume fraction, or say liquid volume fraction. If Cl is 1, it's liquid. If Cl is 0, it's the gaseous mixture. But in the gaseous mixture, we now have another volume fraction that we have defined here as CV. This CV denotes the volume fraction of the vapor in the gaseous mixture. So if the value of CV is 1, that means there is only water vapor present in the mixture. Or if it's 0, that means there is only inert gas present in the gaseous mixture. Now this arrows denotes the droplet is evaporating, and m dot is the rate of phase change. That is a mass of the liquid that is converting into vapor. Now, how do we define this phase change? It's a diffusion limited evaporation model, which is very simple, where you calculate the mass flux that is converting from liquid to vapor with the difference of concentration, or in this case, the vapor fraction at saturated state and in the gaseous mixture. So with the help of this formulation, you can calculate how much change with temperature, since we have a heated surface, and we also solve the energy equation. So the CV saturation is a function of temperature, and the very famous equation called Anton equation you can use to calculate the CV saturation as the temperature changes. So with this evaporation flux, we'll have evaporation cooling, which is quite important. We'll see in the equations now. And another important point to be noted is that in the simulation, we have set on the interface of the droplet where any values where volume fraction is more than 0.9 is to be saturated with the vapor. Okay. So the volume fraction of vapor for any values which is at the interface that is more than 0.9 for liquid volume fraction, we have considered as saturated. So now, since we have looked at the different variables, now I'll just come into the equations once again because so here we have the continuity equation, but since we have an evaporation now, we have the m dot term here, and here you can see the definition of the density, how density is varying in the domain with CL, the liquid volume fraction, as well as CV, the vapor volume fraction. So in our whole domain, we have now three components: liquid, vapor, and inert gas. And so all the properties, just like density, are function of both CL and CV in the domain that is used in the simulation. Okay. So then we have the momentum equation. Quite general. This is the only term that I'm gonna elaborate is this term, which attributes to the thermal Mangoni. So due to evaporation and evaporative cooling, we'll have a surface tension gradient which generates a tangential component of surface tension. So apart from the normal component, we include the tangential component here in the surface force, so to introduce the thermal Mangoni effects. Next, we have the Capillarity equation itself. So it's for the liquid volume fraction CL with the source term with m dot. So since the liquid is evaporating, the mass is transferring from liquid side to the vapor side. It's negative. The sign of the source term is negative. Okay? Now we'll come to the vapor equation. So it's very important here now because of evaporation, now your vapor concentration is changing in the gaseous mixture. So this equation solves basically the advection diffusion of the vapor phase, the volume fraction of vapor, CV, and also the source term m dot. Now, in energy equation, we'll also have evaporative cooling. So there is in energy equation we have this source term as well, and all of these are non-dimensionalized. So you have these non-dimensional numbers: Smith number, Jacobs number, Weber number, Bond number, Rode number, and Pendle number. So just a brief about the boundary condition again. So it's a droplet placed on a heated surface. So the bottom surface is at some temperature, Ts, and the top is at some temperature at and the rest of it is at a bulk temperature, PV. So in X and Y phases in the domain, we have all used, all of the parameters have periodic boundary condition, but for the bottom and the top, we have the durational boundary condition. Yeah. So if you see for the Navier-Stokes, and so if you remember, all of these boundary conditions are defined and in the file called PEC-CRC that is located in the source and setup file itself, where you can mention any kind of boundary condition here for each variable. And also you define the size of your domain with global dimension X, global dimension Z. You select the phenomena in the code that, since you're doing evaporation, we do evaporation here. And this liquid and gaseous limit just to define the area in between where the phase changes happen. And all other similar to, like, as mentioned here, Z, it's X and Y, upper and lower, defines all the boundary conditions for all the parameters in the fetch CRC file. Yeah, so now I think this is the very basic for the evaporation part of the code. I think you all saw the initialized droplet last week, I guess, in Paraview. So I think it'll be easier now if we kind of do hands-on-hands, load some files in Paraview and see the evaporation, see the cooling that is happening due to evaporation on the interface of the droplet. And I have some files already sent to Mayank. You will have an initial file and you will have a file after some time when the little bit of the droplet is evaporated. You can see the comparison and how phase change is happening, and also you can we can go through the code as well for some, like, let's say, to see where the vapor file is and how the vapor phase is solved. So Mayank, so this is it from my side for presentation. I think I kept a bit more time for the hands-on session with Paraview to look at the droplets. It will be easier, and also look through the code a bit, navigate into the files.
Yes, so we can move to the lab, I think. So
yes, so we can kind of do the, so yes.
Yeah.